example. So we started with some simple example first. In the first example, we will try to take the initial type environment and infer the expressions lambda x go to x has some type alpha 1 to alpha. So the inference started off by taking this as input and then the gamma init omitted here for simplicity as input. And we don't know what this is output are. We first go to the next level because this is actually a lambda abstraction, so we apply the abs rule, and that would first requires us example that using algorithm W. We would like to infer under the initial type environment that the program lambda x goes to x has some type, so we're going to infer it. So for now, let's pretend we don't know what this is output. Since this is a abstraction, and we would like to apply the abs rule, and the abs rule says that we first need to generate a type variable, okay, alpha 1, and this is supposed to be a unification type variable, and we would like to extend it, use it to extend the type environment gamma init, and under which we would like to infer the type of the function body, which is x. So then we can apply the var rule, okay, because we can look up from the type environment that x has type alpha 1, and we try to apply the instance function to alpha 1. Since alpha 1 is not a type scheme, so the best we can do is just return alpha 1 as what it is, and therefore the output type for x is alpha 1, and there's empty substitution here, and therefore we can conclude that the type of this program, which is a lambda function that is from alpha 1 to alpha 1 and returning a empty substitution. A more complicated example. So under the same type environment, we would like to infer the type of this program that lambda x go to lambda y return x. And for now, again, let's pretend that we don't know the output. And this is the abstractions. So we did like to apply the abs rule. And first, because of the abs rule, we need to generate a new unification variable called beta 1. And we're going to assign x with type beta 1 and extend it, use it to extend the type environment, under which we're going to infer the type of the body of this lambda function, which is another lambda function. Okay, and again, the abs rule apply here. We would like to create a new type variable, a unification type variable called gamma 1, and we would like to assign y to have this gamma 1 type, and we use it to extend further our type environment, under which we're going to infer the type of the body of this lambda expression, which is x. So in this case, this is a var. We apply the var rule, and under which we can look up the variable x has type beta 1 in this environment, and we apply the ins function to beta 1 that will give us beta 1 back. So the body of the this lambda expression x has type beta 1 with the empty substitution, and it propagates down. And because now we do know that y was actually given the gamma 1, so this lambda function has type gamma 1 to beta 1 with the empty substitutions and propagate down, and we can figure out that, well, this entire program has the type from beta 1 go to gamma 1 and return a beta 1, and with the empty type substitution. Example, let f that takes in an identity function, and then in let g equals to lambda x go to lambda y and go to x, and in g apply to f1 and then apply to f true. So we try to infer the type of this program using algorithm W. So to do that, we apply the let rule first, okay, and then which means that we need to infer the type for this sub-expression, which is the right-hand side of the let binding. So notice that when we try to infer this is exactly what we've seen in our first example number 1, and this would give us the type alpha 1 to alpha 1. And then next we're going to need to generalize this alpha 1 to alpha 1 so that we can give a much more polymorphic type to f. So if we apply the gen function with respect to the gamma init here to alpha 1 to alpha 1, we promote alpha 1 to, for all alpha goes to alpha, So we just, for simplicity, we just drop the subscript because this is a type scheme type variable. And then we need to, given this information that f has a type, this polymorphic type, we would like to infer the type of the in part, which appears as the subproof from 1 in the next slide. So this is this proof of the subproof 1. Okay, for now we use gamma 1 to denote the init gamma that union or extended with f having the type for all alpha, alpha go to alpha. We would like to infer the type of let G equals to lambda x goes to lambda y go to lambda x in G, apply to F1, apply to F true. And we first would need to apply the let rule, and therefore we would like to, under the gamma 1, we would like to infer the type of these expressions. Okay, that is the right hand side of the let binding. We would like to infer the type, and notice that the only difference is that the input gamma is slightly different. The rest is exactly same as our example number 2, and in that example we didn't use anything from our type environment, so it should work the same way as the gamma 1 here. So eventually it will give us the same output, beta 1 go to gamma 1 and go to beta 1 as its output type with empty type substitutions. The next step is that we apply the gen function to this output type for the function G, and we apply gen with respect to gamma 1, and that will promote the beta 1, gamma 1 to beta and gamma. They will become the polymorphic type variable in the type scheme. And then that would use, we're going to use the G has a type, this polymorphic type in the extended type environment to infer the type of the in part, which will be in the subproof 2, and hopefully that will give us the psi 2 as a type substitution output, and hopefully that will give us the in as output as well. We're going to see that shortly. So in these slides we talk about the subproof number 2, and we assume that gamma 2 denote the gamma init extended with f has a polymorphic type for all alpha, alpha go to alpha, and G has a type for all beta, for all gamma, beta go to gamma go to beta. And we consider the expression we will try to infer the type, that is G applied to F1 and applied to F true. And this is actually a app application, so we apply the app rule here. So we need to first infer the type of the function expression, which is f applied to f, G applied to F1 under the gamma 2 environment, and that will produce some T1 and side 3, and then we need to apply side 3 to the gamma 2 and try to infer the type for the actual argument f applied to true. There is some type T2 and psi 4, and these two will be the subproof appear in the next slides, and that will actually eventually give us that the information that T1 here is actually a gamma 2, another new unification variable gamma 2 that returns, and then a right arrow int, and T2 here will be bool. Okay, and then the psi 3 will be a substitution that replace beta 2 with int, gamma 2 with epsilon 1 with gamma 2 to int, and zeta 1 with int, and alpha 2 with int. And for psi 4, which is a type substitution that replace eta 1 with bool and alpha 3 with bool. Okay, so hence psi 5 basically is the result of the MGU of the 2 that will give us substituting delta 1 with int and gamma 2 with bool. Because the delta 1 is actually here, sorry, there is a typo here, this should be delta 1 because it's a unification variable. Okay, and to unify these two, that will give us a substitution that with respect to the gamma 2 as well as the delta 1, and we're going to call this is sci5, and sci5 will be applied to the output type here, and as you can see, this will give us in integer as output type here. And sci2 is a composition of sci3 composed with sci4 and composed with sci5. Next, let's look into detail of these two subproof. Okay, the subproof for this expression, okay, is as follows. So under gamma 2, okay, we like to infer that G applied to F applied to 1 will have some type. So again, this is an application. So we would like to apply the app rule, and we first need to find the type of G, okay, and since G is a variable, okay, it goes here, okay, and we can look it up in the type environment, and we find that actually it's a polymorphic types. Then we apply the ints rule to give it a more a less polymorphic type. So this will become beta 2, gamma 2, and beta 2. So notice that even though these are the type variable, but they are not bound by any type scheme, so they are still considered as simple type. Okay, we're going to apply the G. We're going to give G this type. Okay, the output of this inference would hopefully give us some type substitution to beta 2 and gamma 2 via the MGU. Okay, the next step is that we would like to try to infer the type for the actual argument f1. So under the same gamma 2, we look at this expression. So this is the application. Okay, so we first need to look up what's the type of f. Then we look at this rule here, and from the type environment, we can find that f has type for all alpha go to alpha, and we immediately try to ground it and make it less polymorphic, and we use the int function to produce a simple type alpha 2 goes to alpha 2. Again, this alpha 2, they are unification variable. They are not bound by any for all symbol, so the result is still a simple type. Okay, given this information, now we have looked at the actual argument 1 here. So this is done by the const rule, and the, 1 has type in int and with empty type substitutions. Because of the apps, we need to produce a new unification variable zeta1 that will serve as the return type. And we're going to take alpha 2, go to alpha 2, and int that go to zeta1. We're going to perform a unification on this. So the solution is to replace zeta1 by int and alpha 2 by int. So this would be our output substitution for this step psi6. And if we apply psi6 to zeta1, this is actually integer. So this is the sub-steps of these derivations. So coming back to this app rule, so we have to again generate a new type variable that which serve as the result type, and we know that this part has this type, which is the function type, and we immediately apply psi6 to it, hopefully try to ground some type, but actually doesn't do anything. And then we also need to apply psi6 to zeta1, which gives us int, and right arrow epsilon1. And when we try to unify these two, okay, that will give us we will need to replace beta 2 with int and epsilon 1 with gamma 2 right arrow int. That would be our psi7. So the return result of psi3 would be composing psi6 with psi7, and the output type for this expression will be psi7 applied to epsilon 1, that is gamma 2 right arrow int. In the next slide, we consider a subproof of proving f applied to true has not really proving, sorry, having tried to infer f applied to true has some type bool. And this one is similar to earlier on, that we need to first look at this is the application, and we apply the app rule, and we look up the type of f from the type environment via the var rule, and this is a polymorphic type scheme. So which means that immediately we need to apply the int rule to give it a more polymorphic type. So let's say we ground for all alpha to go to alpha 3, right arrow alpha 3. And again, just to differentiate, alpha 3 is, even though it's a type variable, is a unification type variable. And there's no for all symbol that introduced the polymorphic type scheme here. So this itself is still a simple type. Next, we have to look at the actual argument. True is a constant, so we can infer its type as bool. And because of the app rule, we need to produce a new type variable called eta1 that serves as the output type. And then we're going to apply the MGU function to alpha 3 and to the bool and right arrow to eta1. And this will output us a this will give us a substitution that replace bool we replace eta1 with bool and alpha 3 with bool, and that will be our output substitution size 8. And the output type will be applying size 8 to eta1, which is